Hello! So, today, represent ko yung pinresent ko sa C257 na class namin under Dr. Jaime Hernandez. So, sa part ng course na to, parang kailangan mo mag-present ng paper, anything that involves finite element modeling. So, ito yung pinresent kong paper presented by Murayama, Igarashi, and Tominaga. So, yung abstract ng presentation, the study determines yung snow drip accumulation, yung kung gaano kalalim yung snow sa isang building, gamit yung CFD analysis. Yung CFD analysis ginagamit mo para makapag-simulate ng wind. Then, kapag alam mo na yung wind, given halimbawa yung intensity ng snow, using yung snow drip theory, makukuha mo yung accumulation ng snow. So, in theory, yung computational fluid dynamics, basically, CFD, computational fluid dynamics, more commonly known in its abbreviation of CFD. CFD is basically the finite element modeling of fluid flows. So, sa theory niya, there are two main equations or main equations na kailangan mong considered. First is yung conservation ng mass. So, yun nga, pinapakita ni Maiko Shuu. This is Maiko Shuu from Nisekoi. So, mass, parang sinasabi lang dito na kung ano yung pumasok na mass, yung dapat yung lalabas na mass. So, mass in equals mass out. Wag lang kayong ma-intimidate sa illustration, yung sa mga derivatives na nakikita niyo. So, basically, parang sinasabi lang na dv over dy, parang tinutukoy lang niya yung change ng velocity. Alam mo, may pumasok siya at this velocity. Paglabas niya, nagbago siya ng konti. Yung pagbabagong yun, ibig sabihin, yun yung dv, yung partial with respect to v. So, yung change ni vertical component ni velocity over, tinutukoy yung y. So, yung difference ng y na pinagdaanan niya. So, y nga yung pataas, diba? So, from at this point to this point, yung difference niya in y, that's partial of y. So, partial of b over partial of y is basically yung pagbabago lang niya from this point to that point. And then, si partial of u with respect to x naman, pagbabago niya from this point to that point. Ganun lang siya. So, kapag sinimplify mo na, pag-arrive ka into this equation, yan yung conservation of mass, partial of u over partial of x plus partial of v over partial of y should be equal to 0. Siyempre, dapat walang na-introduce na bagong mass. Since kino-consider naman natin incompressible yung fluid, kaya ganito siya. So, yung second na equation na kailangan i-consider is yung Newton's second law. So, yung forces, sinasabi kasi dun sa Newton's second law na kung ano yung sum of all forces would be yung acceleration ng object. So, yung mga forces na nag-a-apply dun sa fluid basically is the normal stresses and the shear stresses. So, ayan yung following. So, yung normal stresses, yung dun sa gitna dito, yung shear stresses yung nakikita nyo parang half arrow lang. So, kapag kinuha mo na yung sum of all forces, mag-a-arrive ka dito. So, sa fluids, basically parang yung force balance, tinatawag siya, force balance ng fluid, tinatawag as Navier-Stokes equation. So, kapag kinonsider mo na halimbawa yung fluid is a sum ng kanyang average component sa kanyang fluctuating component, syempre hindi naman parang constant na parang mararamdaman mo na bumubugso-bugso yung hangin. So, kailangan mong i-decompose doon. So, mangyayari, meron kang, halimbawa, yung velocity field, mag-decompose siya into u bar, which is yung average component, saka u prime, which is yung fluctuating component. So, kapag sinubstitute mo na siya, darating na siya rito. So, yun nga, si u bar, yung average component, si u prime yung iyong turbulent component. Papansin mo, ng dalawang dulong terms for both u and v, meron siyang na second order na linear na term. So ang problemahin mo na lang paano mo siya i-close. So hence tinatawag na closure problem, kasi kailangan mabawasan mo yung number of unknowns dun sa equation mo. So kung meron ka pang additional unknown, yung meron ka pang u prime, kulang yung equations mo para ma-solve. Basically yun yung sinasabi. So kumukuha si Shuu ngayon ng kodigo. So this came from Reynolds. So sinasabi na yung nonlinear term na yun can be called as Reynolds stresses. Then gagawin mo na lang according kay Business, equate mo na lang siya into the Laplacian of the average velocity field. So ito siya. Ito siya. And multiply mo na lang by a term called mu t, which is the turbulence viscosity. And kapag sinubstitute mo na siya sa Navier-Stokes equation, you arrive into what's called the Reynolds average Navier-Stokes solution. So RANS. Ito yung RANS. So hooray, na-discuss na natin kung ano yung RANS in the first place. Pati yung theory behind everything. So nandun na tayo sa finite element formulation. So sa finite element formulation, either determine mo yung weak form or yung strong form ng equation. So kailangan, ang rule dito, kung ano yung ma-determine mo na, alam mo, ang makukuha mong values ng u, makukuha mong values ng v, makukuha mong values ng pressure. Saan yung pressure? Kasi mamaya, ayun, yung pressure should be in a way kung saan yung buong equation na to will be equal to 0. Yun yung weak form formulation. So integrate mo ngayon yun. So basically nahati siya into what's called the essential boundary conditions and the natural boundary conditions. Natural boundary conditions, sinasabi niya kung paano ba magbe-behave yung fluid dun sa inside ng domain. Essential boundary conditions, parang yung kaduluduluan ng domain, aning dapat niyang maging behavior. So ito si natural boundary conditions, ito si essential boundary conditions. Then we apply yung Ritz formulation kung saan halimbawa yung velocity field mo, kung diniscretize mo siya, halimbawa isang velocity field, diniscretize mo into various points, tas bawat point na yun merong velocity value. Then sinasabi lang niya na yung buong velocity field should be equal nung sum ng mga values na yun multiplied by a weighing function. So halimbawa itong point na to, may velocity siya, halimbawa weighing function niya, yung weigh niya, parang sinasabi dapat na ito 20% ng buong flow, yun yung weighing function. So isa-substitute mo lang siya dun sa equations as psi yung weighing functions, mag-a-arrive ka dito. So sandamakmak na matrices yung mapoproduce dito, namely K1 and K2, K3, K4. Yung K3 is actually yung transient na part. K4 is actually yung how should I call this? Yung shear stresses na part. Yung K5 is yung pressure. K5 and K5 is yung pressure na part along X. Yung K6 na part, yung K5 yung along X na, yung parang boundaries na existent along the domain X. Kung meron mga vertical, Y naman yung yung mamaya i-discuss na. K6 is yung shear stresses din sa boundaries. K7 yung naitintukoy din along the Y. So, hooray, na kuha na natin. Parang madali na lang ba siyang solve? Hindi. Kasi implicit siya. So, ma-determine mo yung vertices, yung matrices in the first place, kailangan alam mo na yung value ng velocity field mo. So, paano mo mare-resolve yung loop na yun? Parang loophole na yun. Paano mo siya masasolve? Gagawin mo na lang, iteratively mo na lang siyang isasolve. Dapat may guess values na. Then, using either Jacobi method, Gauss-Seidel method, or marami pa tayong actually ano to, numerical methods na pwedeng i-implement dito para ma-solve mo iteratively. So, paano mo ngayon isosolve? Tanong ni Rudy Chan. So, start, solution at time n. So, gagawa ka ng mga, yun nga, yung kanina, gagawa ka ng mga linear equations yung ipoproduce nun, sandamakmak na linear equations. And kukunin mo yung updated solution. Siyempre, magagawa mo yung simultaneous equations na yun once meron kang guess values ng velocity field. So, hanapin mo yung updated solution. Kung nag-converge, hindi pa, update mo ngayon yun. Kung yes, check mo yung linearity. So, kung may truncation bang nangyari or wala. Kung meron, which amounts to no, i-re-redo mo ngayon yung non-linear simultaneous equations. So, yung tinutukoy sa linear simultaneous equations, it involves yung meshes mo, which i-discuss mamaya. So, may mali sa mesh mo. Hence, kailangan mong i-redo yung linear simultaneous equation. Kung okay na siya, edi that will be yung velocity field mo at the next time step. So, i-determine mo na yung ipo-project mo na yung flow doon sa next time step. Then, kung hindi pa siya yung yung final solution mo, hindi pa siya yung steady state conditions mo, kung yun na pala yung steady state condition mo, okay, end mo na. Pero pag hindi pa, pabalik ka doon sa start pang next time step naman. Ganun yung solution workflow. So, next na din-discuss is yung drifting snow field. So, sa drifting snow field, basically, lang siya, transport equation. So, parang transport equation is a partial differential equation depicting yung transport and convection and dissipation ng isang passive scalar dun sa isang buong domain. So, para ma-depict mo yun, kailangan alam mo na yung velocity field mo in the first place. So, pag nakuha mo na yung velocity field, ipo-plugin mo siya dito. So, wag naman kayo ma-intimidate dyan. So, nandyan yung mga constants. So, yung UP, nasan ba yung UP dito sa yung velocity ng fluid at point P. So, dito siya ina-apply sa pag-determine ng friction friction velocity. Yung etong term na to is yung friction velocity. So, Kp is the turbulence kinetic energy dun sa point P. Yung Yp is yung distance ng point from the wall. So yan lang, parang taken from the paper of Tominaga, Okase and Mochida in 2016. So, basically, darating lang siya sa point na to pagkuha ng Q total. So, si Q depth, given naman to, madaling mo siyang ma-determine. Ito is actually yung snowfall intensity. Tama ba? Wala rin na lang. So, yung Q arrow is yung erosion na nangyayari. So, for both cases, kailangan mo yung friction velocity. So, yung friction velocity, kailangan mo makuha galing doon sa simulation mo. So, sa pag-setup ng boundary conditions ngayon, paano mo gawin sa CFD? So, yung nasa taas yung itsura ng building, yung dito, ganito siya in-apply sa CFD analysis. So, ito yung meshing na tinutukoy ko. So, kapag malapit mo sa mismong building, medyo ginagawa na siyang pino para iwas yung truncation errors. Kapag medyo hindi naman significant yung flow, hindi mo kailangan i-resolve yung flow doon, okay lang, nalakihan mo yung meshes mo. Siyempre, nagtitipid din tayo sa space, parang sunog PC din to. So, yun nga, yung mga essential boundary conditions, inlet, kung saan mo in-introduce yung flow, saan pumapasok yung flow. Then, yung walls, halimbawa, nasa gilid naman. Kung halimbawa, hindi naman talaga sila dapat nag-exist in the first place, ni-assume mo na, yung wind flow dito, dapat equal dun sa wind flow kapag nag-pass ka na dun sa wall. So, isa-set mo siya as a pre-slip condition, dapat walang shear stress yan para hindi maapektuhan yung tangential na component ng velocity. Then yung ground, since yung ground is a boundary layer, so dun nangyayari yung parang mataas yung vorticity doon. Kailangan ma-depict mo yung kung paano ba siya nagpo-progress. About dito 0, sa ground 0, and habang papunta ka na dun sa flow, mas mararamdaman mo na yung flow. So yun yung boundary layer conditions. So para ma-implement yun, kailangan ilagay mo na no slip conditions. Yung out naman, kung saan lumalabas yung fluid, siset mo lang na zero pressure differential. So walang pumipigil sa kanyang lumabas. Yun yung magsabihin lang yan. His structure, yan nga, parang nakahiwalay siya kay ground. Dito, siset mo para hihiwalay mo lang siya para pag pinopost process mo na, madali mo nang masasabi na itong mga pressure na to kay structure to. So, ang kukunin mo nga dito yung friction flow, saka yung friction flow, yung turbulence kinetic energy, paano siya natatransport, so on and so forth. So, itong pinapakita yung naka-green na line, allowance to ensure flow retardation. So, dapat wala ng vortices once na mag-exit siya dun kay outlet, or else mahihirapan ng konti yung computer mo sa pag-simulate. So, in-implementing yung CFD. So, CFD, then conceptualize mo yung setup, then yung kanina nga yung conceptual kung paano mo ginawa yung wind tunnel kunwari. Mesh generation, yun kung paano mo diniscretize, then ginawa yung simultaneous linear equations, then yung pag-setup ng mga boundary conditions, then yung pag-implement ng numerical simulation, pag-solve ng mga values, then syempre post-processing ng results, checking yung results kung hindi okay, either mali yung boundary conditions mo, mali yung mesh mo, or mali yung pagkaka-conceptualize mo in the first place. So babalikan mo itong mga to. Kung okay na siya, edi halimbawa kung okay na, ito na yung results na kinalalabasan. So parang ginawa nila, since hindi mo naman pwedeng pabago-bago yung, kasi ang realidad is hindi naman constant yung wind speed throughout time. So ang ginawa na lang ng mga authors is ginawa na lang yung various cases, may leeward sa windward na case, tapos at different velocity. Mamaya i-discuss kung bakit. So pag nakuha na nila to, kukumputin lang nila yung friction velocities ng kanina. Pag na-compute na, kukumpute yung snow due fluxes, yung mga Q. And then yung kanina nga, sinabi ko nga na on the assumption, ito yung Monte Carlo simulation na hindi mo na pwedeng i-simulate na paiba-iba yung yung velocity kasi magkakandalaw-ko yung mo. So ginagawa na lang, kukunin mo na lang yung probability distribution function ng wind over dun sa observation time mo. Then halimbawa, sinabi nga 1 meters per second, 40% yung probability, parang 40% of the time 1 meter per second siya, then 25% of the time 2 meters per second siya, and so on and so forth. So i-multiply mo na lang kung ano yung results ng simulation at 1 meters per second dun sa probability niya na mangyari. Then isa-summation mo yun yung parang Monte Carlo na case. So finally, ko-compute mo na yung snow depth na na-accumulate over dun sa observation period mo. So ito yung results, and pinapresent ka ni Shuu over dun sa table. So meron tatlong conditions, A, B, and C. Then yun nga, yung solid lines, yung mga lines is yung CFD results, while yung diamond, circle, and triangle lines are yung actual na recorded state. So medyo malapit naman siya according to the authors. So yun nga yung contributions kanila, applying yung Monte Carlo simulation apart dun sa CFD analysis dun sa pagko-compute ng snow drift. So ganun na lang, parang kaya mong i-simplify. Nga lang, limitations nga, parang yung study, kinonsider lang yung windward sa leeward, parang hindi niya kinonsider yung ibang angles. So ayun, basically, natapos na yung presentation. Ayun nga, si Shuu, yung bubunyi, natapos na yung presentation. So, thank you very much sa pakikinig, and medyo sabaw nga itong presentation. I hope natuwa naman kayo sa pagkakapresent.